Welcome to the Enamena video tutorial about concentrating solar power technologies. This is Unit 3, block number 2, and the topic is the potential for optimization of concentrating solar collectors. My name is Eckhard Lüpfert. I'm working for DLR since more than 20 years in the field of different concentrating solar technologies, over the last years in particular on the optimization of performance of such systems, knowing the details of the configuration and their relevance for the field application. Just to summarize what you know already about the systems, we have mirrors that concentrate the sunlight onto the receiver of a trough collector or any other kind of concentrating solar system. And on this way, from the sun over the mirror to the absorber, we have certain components, and we're looking at their properties and about their potential that enable us to optimize the overall optical performance of our system. First of all, the mirrors. The mirrors reflect the sunlight. The sunlight has a specific spectrum. The mirror has a spectral reflectance appropriate for sunlight, and also specularity is important for reflecting the sunlight. The solar reflectance of mirrors is determined by the direct specular reflectance. It is measured with state-of-the-art equipment. It is evaluated with a spectrum as reference from ASTM G173 and results in the solar weighted specular reflectance. This reflectance value relevant for sunlight is not only interesting in the current state, but it's also interesting for the future. So we're interested in the durability of the mirrors. Optimization of mirrors, of course, also means optimizing their durability. Relevant for the optical performance is the mirror shape. Mirror shape is essential to achieve a high intercept factor of the radiation on the receiver. The measurement of the mirror shape is state-of-the-art and shown in another lecture. The slope of the mirror installed in the concentrating system is the key criterion for the performance. This is shown on this slide. The pictures on the top right side show measurements with the deflectometry system and the analysis and result, the maps of accuracy, the maps of the slope deviation and the focus deviation of such mirrors, in this case of parabolic trough mirrors. And we need this high shape accuracy on a large part of the mirror. These measurements need to cover almost 100% of the area. And in order to optimize the intercept factor, we need to optimize the shape, the slope of these mirrors. The optimization, of course, is done in the series production of the mirrors, but with the support of quality control measurement systems and on the basis of standards for defining the slope accuracy, which are in preparation. What are the benchmarks for mirror panel quality? Solar weighted reflectance for mirrors is in the range of 88 to 96%. Depending on the kind of mirrors. State-of-the-art glass mirrors reach 94 to 95% already. For the shape, we define the slope deviation, the root mean square of all measurement values, for which the benchmark is in the range of 2 to 3 milliradians. With increasing competitors, these shape values get better and better. For glass mirrors, we have focus deviation values for RP3 panels of 8 to 10 millimeters, or even lower, 7 millimeter focus deviation typical value means about 10% of absorber tube diameter. And we know already that mirrors are durable. 25 years in California without relevant degradation are proven state-of-the-art for glass mirrors with silver reflective coating and protective coatings. The receiver, shown here again on this picture, is composed of the absorber tube with certain components around that affect, of course, the overall performance. The size of the bellows and the transmittance of the glass tube are relevant parameters for the overall performance. Not only the absorber itself, but all the components around of the receiver, its geometry, the transmittance of the covers are relevant for reaching optical performance. This table shows some typical specifications for receiver tubes for standard parabolic trough collectors, 4 meters length, 25 kilograms, 400 degrees operating temperature range, and high optical properties, absorptance 96% or even more, and emittance of 10% or even lower at 400 degrees. The diameter of the absorber tube is relevant for the performance. Typical diameters for the parabolic trough collectors are 70 millimeters absorber tube, the glass 125 millimeters around. We have the bellows with about 3 to 4% of cover. We have protection shields, possibly reflector shields. We have a vacuum indicator. We have a vacuum nipple. And all this receiver must be adjusted to the focal line. This graph shows the flow of energy from the mirror irradiated towards the absorber tube. It goes through the glass tube, gets absorbed, and then possibly has some thermal loss effects depending on the properties of the coating, the emittance, the vacuum, the convection. The overall result of any losses in this receiver are the losses from the glass tube to the ambient once this energy is irradiated from the absorber tube. We have measurement methods to determine optical performance of the receivers. Physical parameters are absorptance, emittance, transmittance. Their measurement, however, is difficult, and we don't have appropriate quality specifications. Newest receiver specifications do not require destructive measurement in order to measure optical efficiency, but with a sun simulator, we have a fast test procedure under lab conditions and with appropriate geometric specifications. The overall performance of a state-of-the-art receiver for parabolic trough collectors is more than 87%, including the effects of size, of transmittance, and of absorptance of the tube. Thermal losses occur due to the high temperature of the absorber tube. We can measure them also with a non-destructive measurement. We have test procedures, don't require emittance measurements, and get to appropriate specifications for the receivers. And state-of-the-art trough receivers have loss parameters at 350 degrees of lower than 900 watts per square meter of absorber tube surface. One point of optimization is the overall concentrator geometry. The pictures show how the shape is measured, how the shape is analyzed in slope deviations, and how the maps show the details of the deviation of the shape from the ideal configuration, which give enough information to optimize these quality parameters. Important criteria are the position of the receiver tube, it must be in the center. The deformation under operational load must be low. Wind loads, dead loads, drive forces must be kept low. And the tracking accuracy is important to reach high performance. Quality parameters of the overall collector configurations are the slope deviation or the focus deviation as defined in standards. We can apply such measurements and optimization on prototypes and, of course, in quality control during fabrication, during assembly, and during checks and monitoring of a running solar power plant. I show this graph to identify the relevant parts where optimization is still possible on the current parabolic trough collector technology. It is similar to a graph that is shown in the other sections, and the most striking parameters that you see here are highlighted in specific colors. Reflectance of the mirror, set here to 93%, can be improved to 94, 95, perhaps even 96%. Cleanliness of the reflector can be kept high by regular washing or by anti-soiling coatings. Intercept factor is a matter of optimization of the geometry of the overall collector and all the components. Bellows of the absorber, transmittance of the glass, and absorptance of the tube are a matter of high-quality products that are used in this technology and still some optimization potential in the percent range. A relevant factor is the durability of the overall system. This graph shows again no degradation. Reality looks different. Durability of the optical system, durability of the components are a key to long-term performance of our solar fields. Optical efficiency of a state-of-the-art collector reaches 75 to 78%. Receiver thermal losses are a matter of the quality of the vacuum and the coating of the receiver. In this case, for the receiver, in the range of 5 to 7% are lost by thermal losses, and another 5 to 7% are lost in the solar field and piping. Overall field efficiency reaches 66% in this example, and this is what we have for the conversion in the power block. If you look at the average operation case, these numbers look different, and you see the relevant effect of the thermal losses of the receiver that get higher at lower irradiance values. The rest of the parameters are optical parameters. They stay the same, but the output of energy is lower if less sun is shining. I want to give a short example on the potential that we have if we optimize our solar collectors. An optimization of 1% in optical performance of a mirror is realistic. And for the case of Spain, this is equivalent to 700,000 euros per year of higher performance in the case of a 50 megawatt undersol plant. So we need to care for the mirrors, for their high reflectance, for their precise shape, and for their proper mounting and assembly in the solar field. The graph shows the dependency of the intercept factor as key performance factor of the focus deviation of the quality parameter of our mirror. And you see the reference case in the center with focus deviation of 10 millimeters. You get 100% performance. And with better quality, the output of the solar plant increases by several percent points. The relevant difference can be quantified in money, in particular in the case of high tariffs for the power production. The effect on the annual income or the annual electricity production is shown in this graph, depending on the quality of the mirror. For all the CSP technologies, we have mainly the same kind of optimization criteria for the components. The tracking geometry, on-axis, off-axis, parabolic, Fresnel, the kind of rim angle, the focal distance, the concentration factors, all these influence. The mirror product comes with its reflectance, with its shape and durability. The receiver has its optical efficiency on thermal losses. And this all results the overall output of the solar field. Once we come to the thermal system, we look at piping insulation, at inertia of our thermal system, thermal loss on components, pumping power, and of course on the power block with its performance, the cooling, the startup losses, heaters and transformers. To summarize again, optimization potential of a parabolic trough collector can be found in the components, the mirrors with reflectance and shape to achieve a high intercept factor, and in the absorber with the geometry of bellows, the transmittance of glass, and the absorptance of the absorber tube itself. And improvements in the percent range in these effects gives an increase of the overall optical efficiency of the field and overall thermal efficiency of the field for this peak example. This is one of my favorite pictures showing how important is the optimization. These birds can sit on the glass tube because the thermal losses are low. The glass keeps cool due to the low emittance and due to the good vacuum in the gap between absorber and glass tube. And these birds can sit there on this really operating tracking collector because the intercept factor is high. The radiation reflected by the mirrors tracked to the sun goes onto the absorber tube and keeps the performance of this trough collector high. This is the end of the lecture. Thank you for listening.